Hi there and welcome back. Now we're going to go now and look at the Euler identity in the complex exponential. We've seen in the previous video that we can approximate a function using a series of polynomial functions, and we called that the Taylor series. And we were able to derive the Taylor series approximation for the cosine function, and we've seen that it gives us even terms, so that's terms in 2, 4, 6 and 8. And the Taylor series approximation for the sine function gave us odd terms, so that's the terms in 1, 3, 5, 7 and 9. So the cosine function is an even function and the sine function is an odd function. So let's go and we'll look at the even and odd functions graphically. So you'll see drawn down here part of a cosine function. And if I was to look at the cosine of positive x, so that'll be this yellow line here, and then look at the cosine of the minus x, we'd have this line here, and you can see they're the same height, so it's the same value. So we can say that cos of minus x equals cos of x. Now this is an even function. If we were to reflect this function on the line, the y-axis, then it would be a mirror image. Now I've also drawn out the sine function here. And we can see that if we were to look at sine of minus x, it'll give us this value here, which is a negative value. And the sine of positive x would give us a positive value. So we therefore say that the sine of minus x equals minus the sine of x. So this here is an odd function. Now one of the interesting things about odd and even functions is things that we can, this kind of symmetry, we can use this to our advantage later on in the rest of the course. But one thing to note here is that if I was to integrate an even function from minus infinity to infinity, then the only part that would be left would be this section here. All of the rest of the sections would, one section would cancel with the other section, and you just have this little term here. So if I was to integrate it from plus infinity to minus infinity, I would get an actual value. But if I was to do the same with an odd function, then you could say that all the sections above the line, they all cancel out with all the sections below the line. So if I was to integrate an odd function from minus infinity to infinity, I would get 0, and that's going to be of use to us in future videos. So now what we're going to do is we'll go and look at the Taylor series approximation to the complex exponential. That is an exponential which is raised to a power of a complex power. So the complex exponential is given by e to the ix. Now if we were to differentiate this 1, 2, 3, 4, 5 times, we'll get these values here. So we'll get an I squared, I cubed, I to the 4 and I to the 5. So if we were to look at these, this is going to give us the point x equals 0. It's going to give us f of 0 will give us a value of 1. F derivative at 0 will give us a value of I, and the second derivative would be minus 1, then we'd have minus I, then we'd have 1, and then we would have I. So using the Taylor series expansion, we can write that then as 1 times x to the 0 upon 0 factorial. It would be I times x to the 1 upon 1 factorial minus 1 times x squared upon 2 factorial, and so on and so forth. So therefore we can write e to the ix as a Taylor series approximation of 1 plus I to the x minus x squared upon 2 factorial minus I x cubed upon 3 factorial, and so on. So now what we're going to do is we're going to take this e to the ix, and we're also going to look at the cos x and the sin x, and we're going to compare them. So let's equate the e to the ix with the sin x and the cosine x. E to the ix is written here, and I've rewritten the cos x and the sin x, and you'll note that this e to the ix is made up of the cos x terms. It's also made up of the sin x terms, but there's an extra factor of I in each of the sin x terms. So therefore we can say that e to the ix equals cos x plus I sin x, and that's an important identity and what we really want to get at. Now it would be silly if I wasn't there to take that and then mention Euler's identity. If we were to take the value of x to be equal to pi, Then we could say that e to the I pi would equal cos pi, which would be minus 1. And I sin pi, well, that would give us a value of 0. So therefore we could say that e to the I pi equals minus 1. And that's a famous little mathematical equation called Eulers Identity. Now what we're going to do is we're going to take this here and we're going to see how it can be made to represent or represented by a rotating phasor in the complex plane. So we know that e to the I theta equals cos theta plus I sin theta. We can therefore write e to the minus I theta equals, well, cos of minus theta is the same as cos of theta, we've just seen that. And the sine of minus theta is the same as minus sine of theta. So that's going to equal e to the I theta equals cos theta minus I sin theta. Now if we were to add both of these together, these terms would disappear. We would get 2 cos theta, so we would be able to say that 2 cos theta would equal e to the I theta plus e to the minus I theta upon 2. So therefore when we divide the whole thing by 2, we could say that cos theta can be given by e to the I theta plus e to the I minus theta upon 2. We can do the same thing with the sin theta, in which case we get e to the I theta minus e to the minus I theta upon 2i. Now we can see that graphically, and also I'm going to show you in a graphical calculator as well. So we'll talk over it here and then we'll have a look at it in the graphical calculator and it'll become more obvious. So we've got the two phasors here represented from above. This phasor here, e to the I theta, rotates in the anti-clockwise direction. E to the minus I theta rotates in the clockwise direction. And if we were to add those two vectorially, then they would map out a line along this x-axis, which would be equal to twice the cosine. Similarly, if we were to look at the sine version here, we would have e to the I theta, which would be a phasor rotating in the anti-clockwise direction. E to the minus I theta is this phasor here, which rotates in the positive clockwise. But it isn't e to the minus I theta, it's actually minus e to the minus I theta. And remember, we're talking about a vectorial addition here, so that is equivalent to a vector in the, not in this direction, but in the opposite direction. So these are our two vectors in effect, and they're travelling in opposite directions. And they're going to map out vectorially this line here, which is the y-axis, and it would be 2 sine theta. So let's go and we'll have a look at that in the graphical calculator and it'll all become apparent. So what we've got here is our circle. We've got our two phasors here, one in blue, which is e to the minus I theta, travelling in the clockwise direction, and we've got one in the orange, which is e to the I theta, which is travelling in the anti-clockwise direction. And we produce the vectorial sum, so that you can see the vectorial sum are these two lines here, which maps onto a point on the y-axis. Now as these points move round, this point here will move up and down this line from +2 to -2, so let's just see that happening. And you can see that, if I bring it back to that point here, you can see that happening here. So it's going from -2 to +2, and it's a vector addition of those two rotating phasors. So that's mapping out the twice the sine, so the sine's going to be half of that. So we can do the same thing with the cosine representation. And again we've got our two phasors. If I'm moving back around here, we've got our two phasors. We've got e to the I theta there, rotating in the anti-clockwise, and with the orange one is e to the minus I theta, rotating in the clockwise direction, and there's a vectorial sum which will map out a line along the x-axis from +2 to -2. So let's see that, you can see that happening here. So that then represents twice the cosine. So the cosine is half of that. So finally, here's just a little addition just to make sure that you don't get confused here. What we were looking at there was the x-axis, which was a real number line, the y-axis, which was an imaginary number line, so it was actually IY. So the e to the I theta maps the real number line onto the complex plane in such a manner as it actually maps out a circle or a rotating phasor. Now that's different from saying that this is the real number line, and if we were to take that I away and take that I away, and we would have the real number line here, and we would simply have the cosine function and the sine function mapping out a circle. Okay, they're two different things, and what we are interested in is the mapping from the real number line onto the complex plane, which is given by this complex function r e to the I theta. So the complex function that we are interested in is a equals r e to the I theta, and it's represented by a rotating phasor in the complex plane. Now we're going to come back to this in a future video, and we're going to look at it in terms of time, and we're going to see it represented in MATLAB. But that's all there is for this video, and I'll get you on the next video. Goodbye.